Hi, welcome to lesson 24a, the normal distribution. The goal of today's lesson is to learn how to use the normal distribution curve in regards to the mean and the standard deviation. So the normal distribution is displayed when a histogram will form a symmetrical bell-shaped distribution, something like this. So when we talk about different probabilities of certain things, sometimes they can be skewed right or skewed left, like we've looked at things that maybe could be skewed right, or they could be skewed left, something along that line. But the normal distribution is where we have symmetry, where it's all normally distributed about the mean, which is in the center. We know the mean and the median and the mode are all equal. Everything's all symmetrical and beautiful, and so it looks like this bell shape. And the cluster, the majority of the data is right in the center. That's why we have this big hump in the middle. And then as values go to the extremes, they get less and less and less to the high end, and of course less and less to the low end as well. So this, perhaps we take an example of the mass of, I don't know, geckos or something. No, not the mass of geckos. Let's talk about the tail length of geckos. And the majority of the tail lengths will be in a certain range, and then as certain geckos have longer tails, there's going to be fewer and fewer of those geckos that have longer tails, and on the other end, the other extreme, there will be fewer and fewer of geckos that have shorter tails. So that could be perhaps an example of a normal distribution. We could talk about, of course, the masses of Russian brown bears or something, where again the majority of the mass, the average of the masses of all these brown bears are right in the center, and then the heavier ones, there's fewer and fewer of the heavier ones and fewer of the lighter ones as well. So that's how we would see a normal distribution curve. So there's certain characteristics of the normal distribution curve, and one of them is that it's symmetrical, as we see there. The mean and the median and the mode all fall on the line of symmetry of the curve, shaped like a bell. Ding! And of course it slopes downwards on both sides. It approaches 0 at the extreme, so this is approaching 0 as the values get larger, and approaching 0 as the values get smaller. Now it doesn't actually reach 0, it's just approaching 0. So there's like the horizontal axis here, the x-axis is like a horizontal asymptote where the curve approaches but never certainly arrives, and same thing at the low end. The total area under the curve actually equals 1, and the percent of the data that lies between any two values in the normal distribution is equivalent to the area under the normal curve between those two values. So whatever percentage of values are in here, that equals the area under the curve between those two values. And the notation that describes it, we would say the normal variable x, for example. So x is distributed as the normal distribution, where mu is the mean and sigma squared is the standard deviation. So this is how it's going to be described for the normal distribution curve. So anytime you see something like this, that means it's normal distribution, and we'll get a bell curve like that. Okay? Now, one other thing that we need to be aware of is that each of these, the curve, the normal distribution curve, is always, yes, always made up of these percentages. And each of these, from the mean out to the next segment, this, for example, is one standard deviation away from the mean. This is one standard deviation from the mean, but on the low side. Here is 2 standard deviations away from the mean. Here's 3 standard deviations away from the mean, etc. And it goes on the other side as well. So right in the center, on 1 standard deviation from the mean on either side, is a total of 68.26% of all the data. That's what we'd call kind of average. This is where the big clump of data is, and which means that 68.26% of the area is under here as well. Then we see if we add one more standard deviation away from the mean, we're adding 13.59% on either side of that. So that ends up being, what would that be? Another 27.18 added on to the 68.26. So that's going to be whatever that would add up to be, because I'm not using my mental math at the moment. And then we add another 2.15% on either side of that, where it's up to 3 standard deviations away from the mean, followed by this little tiny bit here that you can barely see, and that area is 0.13% of all the data at the very, very extremes. So as you know, as you can see, the largest clump is in the middle, and it gets less and less and less as you get to the extremes on either end, just like I described before. Okay, and the one important thing here is the definition of 1 standard deviation is the distance from the mean to a point of inflection. And a point of inflection is something that we'll be using in calculus soon. And that point of inflection is where the curve changes from concave down. You see this concave down here to concave up. So this is concave up here, this is concave up here, this is concave down. And where it changes from concave down to concave up, that's called a point of inflection. And the point of inflection, that horizontal distance, then gives the distance of the standard deviation from the mean to that point. So that defines what the standard deviation is, and then from there we just continue adding standard deviations away from the mean on the positive side and on the negative side. So that's basically it. And notice, of course, here in the middle, mu, that's the mean, this is right down in the middle of the curve. So that's basically the long and the short of it. We're going to be using a lot of this, so you're going to have to know this fairly well in next lessons and examples. And so now that you finish this, I'd like you to take a look at example 1 on page 634, and then take a quick look from page 634 to 635, exercises 2 through 5 and 7 to 13 before coming to class tomorrow. So this is the little lesson on the normal distribution curve. Thanks for watching, and we'll see you in class.